Hello everyone, myself B. Vijaya, lecturer in chemistry, Indira Priyadarshini Government Degree College for Women, Nampalli, and we are discussing the chapter called Coordination Compounds. In this coordination compounds, we have already discussed the valence bond theory, its salient features of the valence bond theory, and how the relationship takes place between the coordination number and shape of the molecules. So with their applications also we have seen with coordination number 4, that is square planar and tetrahedral complexes, and coordination number 6, that is octahedral complexes. The next one is the because of the drawbacks of valency bond theory, and the other theory we are discussing, that is the crystal field theory. And in crystal field theory, which is explains about the shape of the d orbitals. Here the d orbitals plays a very important role in the crystal field theory, and the splitting of the d orbitals will be takes place in the presence of the ligand field effect. So how this will takes place in the octahedral complexes, tetrahedral complexes, and square planar complexes we have seen. And the spectrochemical series also, the spectrochemical series also given by the this crystal field theory. So what is the use of the crystal means the spectrochemical series is we can know what are the strong field ligands and what are the weak field ligands. So in the presence of strong field ligands, the electron pairing will be takes place in the lower energy level only, and in the presence of the weak field ligands, the electron pairing does not takes place, means the fourth electron will enter into the Eg orbital. So moderate ligands are acts as in between, means they are as per the conditions they works. So this is about the spectrochemical series, and we have seen the applications of the this crystal field theory with various applications we have seen. And crystal field stabilization energy calculations we did already. The energy calculations are four we have in our syllabus. So calculation of crystal field stabilization energy of an octahedral complexes with strong field ligand in the presence of strong field ligand, and calculation of the crystal field stabilization energies of a octahedral complexes with in presence of weak field ligands, and we have discussed till here. So, this all these we have discussed in my last videos. If you did not watch in my videos, please watch them first. And today's our topic is the calculation of crystal field stabilization energy for the tetrahedral complexes. So, for the tetrahedral complexes means what? Tetrahedral complexes means here, that is a coordination number 4, right? Coordination number 4. Uh, coordination number 4. Coordination number 4 complexes, and in the presence of strong field ligands. Strong field ligands means what? When the ligands approaches to the complexes, the coordination complexes, the splitting of the d orbitals of central metal cation will be takes place, and in the presence of this strong field ligands, what happens? The electron pairing takes place in the lower energy level only. Lower energy. Lower energy. So first thing we need to know, we already discussed this splitting of the d orbitals in tetrahedral complexes. Once again I am giving this one. So the metal cation is having a 5d orbitals, right? 5d orbitals. The names of these orbitals are dxy orbital, dyz orbital, dzx orbital. zx orbital, and this orbital is dx square y square orbital, and this orbital is dz square orbital. And these orbitals, in the presence of ligands, they splits into two types, right? So in what way they splits? Because these are the tetrahedral complexes, and all the ligands are approaching the central metal cation in between the Cartesian axis, not along the axis, right? So in Cartesian, through the Cartesian axis, they are approaching the central metal cation. So how they approach us is, for example, what is the means to understand the structure I have given in the cubical structure manner. So this is a cube. So when the tetrahedral molecule is inserted in the cube, so this will be one bond this side and another bond this side, another bond this side, another bond this side. So this will be the structure of the this tetrahedral structure, right? Tetrahedral structure is having this kind of the structure. So if you see here, this is the x-axis, this is the y-axis, and this is the z-axis. And if you see here, there is no ligand is approaching through the axis, Cartesian axis, right? So there is no ligand is approaching through the Cartesian axis, but the ligands are approaching in between the Cartesian axis here, in between the Cartesian axis. So that is the reason the means which one will be the least energy now, because they are having the ligands which are having a which are orienting in between the Cartesian axis will acquire more energy, and the orbitals which are present on the axis, which are orienting along the axis, they are having a less energy. So here, which orbitals are orienting along the axis, we know that dx square y square dz square orbitals. These two orbitals are orienting along the axis, right? Orienting along the axis. So, for example, this is the x orbital, this is the y orbital, and this side, this perpendicular one, it will be the z orbital. So, for our convenience, I am writing like this. So, this is the x and y orbitals, and four lobes of the d orbital, if present along the Cartesian axis, this is called as a dx square y square orbital, and dz square orbital will be the this one, right? So this is the dz square orbital. Two lobes are along the axis, along the z axis, and this saucer shaped orbital, one orbital is there. So this is the dz square orbital, and these two orbitals are along the axis, orienting along the axis, so that here there is no ligand is approaching through the x-axis, y-axis, and z-axis, but they are approaching uh, through the means in between the Cartesian axis. So what are the orbitals are orienting in between the Cartesian axis? These three orbitals. So these three orbitals are directly repelling the ligands here, right? Ligands, so that their energy level will be increases. So T2G orbitals are gaining more energy than Eg orbital. Eg orbital acquires less energy here. So whatever the electron will enter into this d orbital, d molecule, means d orbitals of a central metal cation, they will first enter into the Eg orbital, unlike our octahedral complexes. So here I'm writing. So yeah, serial number, that means number of electrons, I'm writing present in the complex, and electron electrons present in Eg orbital now, right? So Eg orbital, small e we need to write, or a big E, capital E also, no problem. So electrons present in Eg orbital, electrons present in T2G orbitals, and crystal field stabilization energy associated with this electron. And if one electron is there, so in the xy orbital I am keeping one electron here. If one electron is there, so this electron, which enter into a Eg orbital, right? So this will, after splitting of the d orbitals, the electron will enter into this one. So here, in order to understand betterly, uh, these are the Eg orbitals and these are the T2G orbital, and one electron will enter into this Eg orbital. So what is the energy associated with this one? So Eg orbitals are decreased by the energy minus 0.6, right? Minus 0.6 delta T, and this T2G orbitals, each one of the T2G orbitals were increased by their energy plus 0.4 delta T. So this is completely converse to the octahedral crystal field splitting, right? So in that, the T2G orbitals are lesser energy than the Eg orbitals, and T2G orbitals are having a minus 0.4 delta naught and Eg orbitals plus 0.6. But here it is completely reverse. So this is having minus 0.6. So only one electron is there and one electron is having a minus 0.6, or otherwise just like a octahedral complexes how we have seen. So in same manner we can we can take one formula also. So what is the formula here? I am going to give you a formula for this. So formula for the tetrahedral complexes is minus 0.6 into the electrons present in the Eg orbitals plus 0.4 into the electrons present in the T2G orbitals. So this is the formula here. This is the formula. And so it's not bright color, right? This is the formula we need to remember for the tetrahedral complexes. We can use this formula for either weak field ligands or strong field ligands. This formula is useful to calculate the crystal field stabilization energy values for this complexes. So as per this formula, what is the formula here? Minus 0.6 into the electrons present in the Eg orbitals plus 0.4 into the electrons present in the T2G orbitals. So how many electrons are there? Only one electron is there. So minus 0.6 into 1 plus 0.4 into, there is no electrons, empty orbitals are there. So this will be the 0 because T2G orbitals are not having any electrons. So since there are no electrons, 0 electrons are present, 0 into 0.4 will be the 0 only, and the value will become the same, that is minus 0.6. So I am writing the same value here, minus 0.6 delta T. And the second one is second electrons. If the second electron is enter, where it will enter? So as per our Hund's rule of Bohr principle, etc., etc. So we need to first fill the one electron in each orbital, right? One electron in each orbital. Then only pairing has to be takes place. So according to this those theories or those principles. So the second electron is entering into the Eg orbital, one of means other Eg orbital, second Eg orbital. And is there any electrons are present in the T2G orbital? No electrons are present in the T2G orbital. So here this will be 0 only, this value. And this electrons, how many electrons are there? Instead of 1, here I am taking 2 for the second electron. So what will be the value here now? Not this. So this will be equal to minus 1.2, right? So minus 1.2 delta T electrons. And the third electron, where the third electron will enter now? So the question comes here. So the third electron, where it will enter? So since it is a T2G, means a tetrahedral complex, and here two electrons already, this lower energy was filled, half filled. And third electron, where it will enter? So I'm writing the two electrons, last two electrons, and third electron where it will go. So here now we have to see for what is the field strength of the ligand. So what is the field strength of the ligand? It is a strong field. Strong field means the electron pairing takes place in the lower energy level only, so that the third electron will enter into the Eg orbital only. Now what is the formula? This is the formula, and just apply this formula. Minus 0.6 into how many electrons are there in the Eg orbital? 3 electrons. And is there any electrons are present in the T2G? No electrons present in the T2G. So 0.4 into 0, and minus 0.6 into 3, that will gives minus 1.8 plus 0. So what is the value? Minus 1.8 value. So the crystal field stabilization energy for this third electron will be minus 1.8. And fourth electron, where it will go? Obviously the Eg orbital only, so that the full pairing of the Eg orbital took place now. So but here the T2G orbitals are still, they are empty orbitals only. So how many electrons are there now? 4 electrons are present in the Eg orbital, and plus 0 electrons present in the T2G orbital. So minus 0.6 into 4 will be, what is the value? Minus 6 fours are 24, right? 2.4 minus 2.4 will be the, minus 2.4 will be the this value, maximum value. Okay, for the Eg orbital, means crystal field stabilization energy, when this tetrahedral complexes are having a 4 electrons. Okay, in the presence of strong field ligands. And fifth electron, where it will enter? So there is no place here. The maximum of filling of the electrons in the Eg orbitals, means each orbital will be 2 only. So Eg orbitals are completely filled. So 2 electrons here, 2 electrons here. Now the fifth electron will enter into the T2G orbital only, right? T2G orbital. So now what will be this calculation now? Now here minus 0.6 into how many electrons are there? 4 electrons are there. So plus 0.4 into how many electrons are there in the T2G orbital? 1 electron. So this value already we calculated here for the 4 electrons. So minus 2.4 plus 0.4. So how much it will give? Minus 2.0, right? So minus 2.0. That means if the electrons will increases in the T2G orbitals, so that this crystal field stabilization energy values will be decreases as increase in the number of electrons in the T2G orbitals. So the sixth electron, where it will enter? Where it will enter? So 2 electrons are here, 2 electrons are here. So the second electron, that means the sixth electron will enter here, and now it becomes 2, right? T2g orbitals are having a 2 electrons, and the remaining one will be the same, so it will be minus 0.8, minus 2.4 plus 0.8. So how much value it will be? Minus means 2.4 minus 2.4 plus 0.8, this will be the minus 1.6, isn't it? Okay, minus 1.6. And the seventh electron, where it will enter? The seventh electron, where it will enter is, so the T2g orbitals, each one of the T2g orbitals gets one electron now. So minus 0.6 into 4 plus 0.4 into 3, right? So this is the minus 2.4, and the plus, this will become sorry, 1.2 plus 1.2. Okay, 4 3 is a 12, so point is there 12, 1.2. So what will be the value? Minus 1.2. So minus 1.2 value. And eighth electron. So eighth electron here. These are the two paired electrons. And now the pairing will start in the T2g orbitals also. So now 4 electrons. 4 electrons means, let us rub this one. Okay, so here 4 electrons are present in the T2g orbital. So this will become 1.6. So minus 2.4 plus 1.6. So what will be the value here? This will be minus 0.8, right? Minus 0.8. And the ninth electron, where it will enter? The ninth electron will enter into the, means the pairing of the another T2g orbital will be takes place, and this orbital is unpaired electron. So now this is having minus 2.4 value, this value will gives, and here, so how many electrons are there? 5 electrons are there, right? So plus 2.0. How much the value here? Minus 0.4 value we will get. Minus 0.4 value. And if the 10th electron is also there, the 10th electron is also there. So two pair of the electrons, 1, 2, 3, 4, 5, 6. All the electrons are present. So this will become 6 now. So minus 0.6 into 4 will be minus 2.4, and 0.4 into 6 will be plus 2.4. So this will becomes 0, right? So 0. What is the minimum value for a minimum crystal field stabilization energy? When the complex is having a 10 electrons, that is having a 0 crystal field stabilization energy, and when it is having a maximum, when it is having a 4 electrons, the value will be a maximum crystal field stabilization energy value will be a maximum. So this will be takes place in the tetrahedral complexes in the presence of strong field ligands. Is that clear? Okay. So next we are going to calculate the crystal field stabilization energy for the tetrahedral complexes, that means coordination number 4 complexes, right? With weak field ligands. So what are the weak field ligands are there? What are the weak field ligands are there? What are the weak field ligands are they? The weak field ligands are like water molecule and OH minus ion and all the halogens, right? So these are the molecules which are the weaker field ligands. And for the weak field ligands, there is no electron pairing takes place. No electron pairing takes place in the uh, lower energy level, right? So the third electron will enter into the higher energy level only. So what is the crystal field splitting takes place in the tetrahedral complexes as I discussed just now. So these are the 5d orbitals of the tetrahedral complex, means central metal cation, and the Eg orbitals acquires a less energy than the T2g orbitals here, right? P2G orbitals, and these are separated by the energy barrier in such a way that Eg orbitals are having a lesser energy than they decreases their energy by minus delta 0.6 into delta T, and T2G orbitals are increase their energy by plus 0.4 delta T values. So this will be the crystal field splitting takes place in the tetrahedral complexes. And what is the formula here? Minus 0.6 into the number of electrons present in the Eg orbitals plus 0.4 into the number of electrons present in the T2G orbitals. So here I'm writing here the number of electrons present in d orbitals, the number of electrons present in the d orbitals, and the number of electrons present in Eg orbitals, and the number of electrons present in T2G orbitals, and crystal field stabilization energy values. So, if one electron is present in the d orbital in this way, one electron is present, where it will go? Obviously, it enters into the Eg orbital only, right? So, Eg orbital is having a one electron, right? One electron, and there are no electrons present in the T2G orbitals. Empty orbitals will be there. And what will be the energy associated with this one electron here? Minus 0.6. Why? How it will be? So minus 0.6 into Eg orbital is having one electron, and there are no electrons present in the T2G orbital. So this whole thing will become 0, right? 0, and the value will become minus 0.6 into 0 will be minus 0.6 only. Sorry, plus 0 will be minus 0.6 only. So minus 0.6 value. And second electron, two electrons present in the d orbitals in this way, right? So where it will enter, this will enter into the lower energy state only. So lower energy state, that is the Eg orbitals, are having a two electrons in each, right? Means one electron in each. So what will be the value now? So this will become 2, this will be the 0 only. So what is the value here? So minus 1.2. This will be the value. So minus 1.2 is the value, crystal field stabilization energy for the two electrons present in the d orbitals. Now tell me, what is the third electron will do, where it will go? So whether it enters into the Eg orbitals or T2G orbitals, since it is having a two electrons, so where the third electron will enter? Now we have to see for the weak field ligand or strong field ligand. If the weak field ligand is present, so no pairing, no electron pairing takes place. The third electron will enter into the T2G orbital. So this will be the electronic configuration in the tetrahedral complexes with the weak field ligands. So what will be now? What will be the crystal field stabilization energy? Let's rub this. Okay, so what will be the crystal field stabilization energy? Let's calculate now. Minus 0.6 into e.g. orbitals are having a 2 electrons plus 0.4 into 1 electron present. So this value we already calculated, minus 1.2 plus 0.4. So here sign conventions are opposite. This is the minus symbol and this is the plus symbol. So if we remove 0.4 from minus 1.2, we will get minus 0.8. Right? So minus 0.8. This is the crystal field stabilization energy value for the 3 electrons present in the d orbitals. And now if the 4 electrons are present, where it will enter? Similar to the third electron, it will also enter into the another orbital of the T2G orbital. So the T2G orbitals now having 2 electrons, right? So here 2 electrons and here 2 electrons. And once again, let us calculate. So minus 0.6 into 2 electrons present in the EG orbitals and 0.4 into how many electrons are there in the T2G orbitals? 2 electrons here also. So this will give the minus 1.2 value plus 0.4 into 2 will be the plus 0.8. So how much the value will be? What will be the difference? It is equal to minus 0.4 value, right? Minus 0.4 value. And if the fifth electron present, so for the fifth electron 5 electrons are present. So this T2G orbitals, now each one of the orbitals are having a half filled electronic configuration, that is every orbital is having one electron in each. So what will be the calculation now? So this will become 3 and this I am rubbing and here I am rubbing. So here the 3 electrons are present in the T2G orbitals, right? T2G orbitals for the fifth electron which will enter into the T2G orbital, 3 electrons are present. 0.4 into 3 will be the plus 1.2. And what is the value? What is the difference here? The sign conventions are opposite to each other, same values are there. So it will be a 0 crystal field stabilization energy value. And for the sixth electron, now where the sixth electron will enter? The sixth electron is in the d orbital here. So where the sixth electron enters, since all the EG and T2G orbitals are having one electron in each. So the sixth electron will enter into, now the pairing will be takes place, and that is also in the lower energy state, that is EG orbital. So sixth electron will enter into the EG orbital only. So here one pair is there, one unpaired electron is there, and 3 unpaired electrons are there, right? So now this will become 3, right? And so minus 0.6 into 3 electrons are there in the EG orbitals, and in T2G orbitals 0.4 into 3 electrons are there in the T2G orbital. That means each one of the electron is carrying a 0.4 energy, right? And minus 0.6 into 3, that will be minus 0.8 plus 1.2. So what will be the difference between these two values now? minus 0.6 values, right? So minus 0.6 value. And seventh electron, where it will enter? So here only the seventh electron, here I am showing seventh electron is there, and that will enter into the Eg orbital only. So now in Eg orbital there are the four electrons, right? Four electrons now. Four electrons. So better I will rub this one and then I will write. Okay. So now how many electrons are there? Four electrons are there in the Eg orbital, and there are the three electrons are there in the T2G orbital, and each one of the electron is having a 0.4 delta T energy. So here the four electrons, each one of the electron is carrying a minus 0.6 energy. So this value will be same, 0.4 into 3 will be plus 1.2, and minus 0.6 into 4 will be minus 2.4, right? Minus 2.4 plus 1.2. So what will be the value? Minus 1.2 value. So now the crystal field stabilization energy values are increasing, right? Increasing as the number of electrons are increases in the Eg orbitals. So now the eighth point, now the eighth point. So here four electrons are entered. Eighth point, here I am pairing up. Now four electrons are over now. This is fully filled electron, and the next electron will enter, eighth electron will enter into the T2G orbital. So now again the value will be decreases. Why? Because there is a one more addition of the electron is taking place with the eighth electron here. So now it will become 4, right? So this value will not change now. So better I will rub this, then it will be clear for us. So minus 0.4 into, oh yeah, 4 electrons are present, and minus plus 0.4 into 4, that will be plus 1.6, right? Plus 1.6, and this minus 0.6 into 4, that will be minus 2.4. So what will be the value? Minus 2.4 plus 1.6. So the value will be uh, 0.8, right? 0.8 minus 0.8 value, right? So minus 0.8. And the ninth electron, if the ninth electron, where it will enter now? So here two electrons, so ninth electron, first I will fill here. Ninth electron will be paired up with this electron in the T2G orbitals. So similar way here also I am showing this pairing will be takes place in this way. One unpaired electron is there. Now this is the fifth electron, and it will become 2.0 now. 0.4 into 5, right? 0.4 into 5, so 2.0. And what will be the difference? Minus 0.4. So this will gives the crystal field stabilization energy value, that is minus 0.4. And if all the 10 electrons are present, so the crystal field stabilization energy, what will be? So here this energy level is equal to this energy level now, right? So here all the pair of the electrons taking place here, and better I will rub this one. Okay, So this will be 6 electrons. So minus 0.6 into 4, that is minus 2.4, and plus 0.4, because each one of the electron present in the P2G orbitals carries a plus 0.4 energy into 6 electrons. How many electrons are there in the T2G orbital? 6 electrons. So this value will give the plus 2.4. So minus 2.4 plus 2.4, that will give the 0. So if you see here, the crystal field stabilization energy for the 5 electrons and 10 electrons, that is 0 value. So it is a minimum value, that is the 0 crystal field stabilization energy values. And if you see the remaining values, all the remaining values are in the minus only, right? Minus only. So if you compare, where means here, see here, that is crystal field stabilization energy values, this is the maximum, and for the 10 electrons this is a 0, and all the values are minus, negative values only. So you see now here also. So for the weak field ligands, for the 5 electron and 10 electrons, this value will be the 0, and if you see, if you check, all the values are, remaining values are negative ones, right? So for the strong field ligand, for the 6th electron it is maximum, that is minus 2.4, and for the 10 electrons it is 0. So this is all about the calculations of crystal field stabilization energies of the tetrahedral complexes, with means in the presence of strong field ligands as well as the weak field ligands. Thank you for watching.